So, we've learned about the magnetic field, magnetic forces, and today we start a new area of study which called generation principles, how electricity is produced. And so, let's consider first next experiment. We have a galvanometer or microammeter which measures small currents, and there is nothing connected to it except the coil. There is no power source or anything like this. And there is no current. Now I take a magnet and I bring it in. As you can see, I move it in, there is some current, move it out some current. Now I will do it faster.
No way.
And as you can see, there is a current. When I move a magnet, current is produced. Where it's coming from? It's coming from the phenomenon that's called electromagnetic induction. And to understand electromagnetic induction and put some quantity to it, let's introduce another physics quantity called flux, or magnetic flux, which is equal B, magnetic field, times area of the coil and times the cos of the angle between the plane of the between the normal to the coil and magnetic field. So if we have the coil positioned,
What did you say? A was again?
B is magnetic field.
No.
Area is, we have a coil. Let's say this is a coil. And if magnetic field is this direction, coil positioned like this, this is a normal to the coil. What the angle between magnetic field and the coil? And
90.
normal, not 90. So cos 90 is 0. So it's 0 magnetic flux. If we have like this position, we have magnetic field, we have a normal, so perpendicular to the plane of the coil. What angle equal now? Between magnetic field and the normal?
0.
0. Cos 0 is 1. So we have the maximum magnetic flux going through the coil at that position. And it has a special unit of measurement. It's called Weber. Magnetic flux measured in Webers.
Is that named after the famous physicist Michael Weber?
Isn't it Weber?
If you're talking about famous physicist who discovered magnetic induction, his name Michael Faraday.
Oh, Faraday's law.
Yes.
Mr. B,
And
Mr. B, what
yes.
did you say the angle was between again?
angle between the magnetic field and normal to the coil. Normal. So normal is perpendicular. And so, and what Faraday discovered, that EMF, now what is EMF? Let's recall from last year what is EMF. Is voltage, electromotive force, which is voltage, but in which case we're using the words EMF, not voltage. When you're talking about which particular voltage? Power source. Power source.
I see.
You cannot say about EMF across the resistor. It will be wrong, but you can say EMF of the battery, for example. So when we say EMF, we mean voltage, but voltage of the power source.
What does WB stand for again?
It's a unit of the magnetic flux, Weber. And Faraday's law, who discovered this phenomenon, when the magnetic field through the coil changes, the current is produced. That's called electromagnetic induction. But more exactly, when flux through the coil changes, the current is produced, and EMF, this letter means EMF, equal N number of turns because it's produced EMF in each turn. And when we have turn they connected in series, total EMF we add all of them, so we multiply by number of turns. Number of turns, number of loops of the wire. And we have a rate of change of the flux. Change of flux over the change of the time, over a period of time over which this change happened. More correctly will be, and majority of people in this class already know what the differentiation is, and if you know, that will be very helpful to solve some problems. If not, you still will be able, but it will be a little bit more difficult. The problem will be E equals N derivative of the flux over time. That will be the that will be like what EMF is produced. This is average. This is instance of time.
So instantaneous is average.
This is instantaneous EMF. This is average EMF.
Is EMF just voltage?
Yes, of the power source, voltage of the power source. And we have now this coil becomes a power source because we produce current, we produce EMF across it. So what can change, what can be changed, because we need to have this current produced, the EMF produced. To have EMF produced, we need to change in flux. What can be changing when we're talking about flux?
Magnetic field.
Magnetic field, and that's what's changing in this case. When I'm moving magnets closer or further away, I'm changing magnetic field through the coil. Also, what we can change? Area. I cannot change area of this particular coil. We'll do it on the
You
simulation.
mean surface area or like outside area?
Yeah, how's the area?
This is a coil.
Yeah.
And the area of this is the area. Or in this case, area will be this area. Will be area of this. This is the area of the coil.
So
In this case, it's area of the circle.
Okay.
So not in the wires.
It's not cross-sectional area of the wire. It's area of the coil. Area of the coil.
Oh, that's just.
In this case, it will be area
Oh,
of the
so
circle.
not the like number of you don't include number of turns, it's just the
For area, no.
Just
Area is cross-sectional area of the coil.
cross section. Okay.
Yes. Area of the coil. And also we can change angle. And changing of angle I can demonstrate here. Because here I have magnet and I have a coil between the magnets. And what will be changing when I will rotate the coil? Angle will be changing. When I will be rotating coil, angle will be changing. And observe what's happened when I will rotate the coil. We have light on. I'm producing electricity. Because I'm rotating, I'm changing the angle between the normal of the coil. There is a coil here. When I'm rotating normal, magnetic field stays the same of this magnet. And I'm changing angle, so I'm changing flux through the coil, so EMF is produced. Now, often in the textbooks, you see this formula has minus in front of it. At the moment, we don't look into this minus, we look into a little bit later on. But this is magnitude. What this minus means, and we will add it a little bit later on. Magnitude of the generated EMF is determined by this formula. Rate of change. And watch, say rate of change. If I move this slow, I don't have. But, okay, you know, majority of the faults of electricity in any electrical system is contact, somewhere lost contact. So So that's what happens here, why it was not working. So when I'm moving slow, we have a small current. When I move faster, I produce much bigger current. Why? Why is that?
Change.
Rate of change will be much bigger. The bigger rate of change, the bigger EMF is produced.
So if you hold it stationary inside, it's going to go back to zero? Yeah.
No change, no current. We need change of magnetic flux
There
through
will
the
be a
coil.
change. There
Huh?
will be, even in 1,000 seconds, there's still a change.
What do you mean?
Yes.
As soon as-
If we will have this very big,
Huh?
it still change. If you say this will be 1,000, will still change. 1,000. Tiny current that we might will be unable even to measure. Make sense? So that is a magnitude. So magnitude of created EMF or induced EMF is depends on the rate of change of the flux. Let's do some virtual experiment.
Wait, Mr. B, what's the flux? Like, what is flux?
Flux is magnetic field or strength of magnetic field times area of the coil
No, but he means like what?
times n between them. In other words, sometimes flux can be determined, say, as a number of the lines of magnetic field penetrating the coil.
Yeah.
So, here we have a coil and we have a magnet. And I can move magnet, as you can see. When magnet not moving, no current. As soon as I move in magnet, you see, the light becomes on. Now, if I will make bigger, stronger magnetic field and area of the coil, if I make area bigger, and I will add more turns, see what will be now. You see how much brighter is light produced. It's a little bit redundant, this app at the moment. And now we can see how the actually most of the electricity, at least at this stage in the world, is produced. What is how electricity that coming to your homes is produced? This is how the electricity is generated on the power plant. And all power plants have the same principle. Is it a coal burning, or it's a nuclear power plant, or it is hydropower plant where the water falls? The thing is, we have a coil and we have a magnet. If the only thing we need now to rotate, as soon as it rotates, as you can see, electricity is produced. And that's how electricity is produced. So the only difference is what rotates the coil. In the coal burning power plants, coal burns, produce a powerful flow of steam, which is rotating the coil. In the nuclear power plant, the steam produced from the heat from the nuclear reaction. And so nuclear reaction in the nuclear power plant, that what should Australia be developing? Because they are so much, they produce pretty much close to zero of the carbon dioxide, so they're not contributing to the climate change. And that's what should be done, and hopefully Finally Australia will understand and will start. And we are positioned better than anybody in the world for the nuclear power plants, because we have uranium, plenty of uranium, which we just sell to other countries who produce energy from this uranium. And we have plenty of space where we can safely, with a very low seismic activity, no like earthquakes or snow. In the desert, we can safely put store nuclear waste, and we're not developing it. It's just unbelievable. And when we're talking about renewable energy, for example, all those solar panels, they have not very long lifetime, and they cannot be recycled. So quite soon we will face a big problem where to store them, and it will be a huge amount of them, because they don't have a long, really. They say that it's 50 years, but there is no anything that supports that. So that we'll have soon problem where to put all like old solar panels, and will be a lot of them. It's one of them. They are with the wind power station. They actually made bad impact on ecology as well, because they actually killing birds and, for example, and so on. So it's not like the renewable energy can solve our problems. In reality, it's at this stage, it's a nuclear energy. The best one will be the nuclear fusion reactors, but we don't have them yet. We're working on that. Now, coming back to the Faraday's law. As you could see, the current changes its direction when it's moving in and out. Why is that? And then we have Lenz's law. We looked into the Faraday law. EMF equals N change of the rate of the change of the flux. And now we will add minus. This minus called Lenz's law. This is a Lenz's law. Yes.
Is the original one Faraday's law?
This is Faraday discovered electromagnetic induction. When the magnetic flux through the wire, through the coil changes, there is EMF produced and current flow if the circuit is closed.
Can you spell Faraday?
F-A-R-A-D-A-Y.
Why does it matter?
Is it Allen instead?
Mr. V said this.
I believe that
Mr.
this is correct. Am I correct? Yes.
Mr. V, so without the minus, it's just a magnitude.
No, minus, Faraday's law is a magnitude. Minus is the direction of the current.
Minus is direction.
And now, what Lenz's law says? Lenz's law says that induced current directed in the way that magnetic field produced by this current, because as soon as we get current, every current produces magnetic field, right? So when you induce current starts flowing in the coil, it creates its magnetic field as well. So magnetic Lenz's law, that the direction of the induced current is that its magnetic field opposes change that created this current. So it's always trying to oppose. So how we apply Lenz's law? Steps that you must follow. And let's consider the examples. Let's say we have a coil which we move in. Let's say we have magnetic field into the page, into the board. We have magnetic field. And we have a square coil. We have a square coil which with the, and let's say strength of magnetic field equal, let's say, 0.2 Tesla. Let's say area of this coil is 100 square centimeters. Can we use square centimeters in our calculations? No, we need to turn it into the meters. What it will be in the meters? How many square centimeters in 1 square meter?
How times sense of
0.01. It's 0.01 meters squared.
That will be 0.01. 1 square meter is 10,000 square centimeters. So 0.01 meters square. And what will be the angle now between the, it's completely now outside, we'll start to move it inside.
0.
What is the angle between the normal to the coil and magnetic field will be 0.
Why
So-
0?
Because it's
Normal is, let's say, perpendicular, magnetic field this way,
Oh,
angle is 0.
Isn't the normal like
No, normal is perpendicular to the plane.
like
Let's say it's normal into the board.
Okay.
why
So, angle 0.
don't.
Now, what will happen when we move this coil? So to have area of 100 square centimeters, what should be the size? One side of the square, what should be the side of the square? 10 centimeters or in meters? 0.1 meter. And let's say we're moving it in with a speed of, let's say, 0.1 meter per second, moving it in. So it's just at the edge of the magnetic field and we're moving it in. Let's find how much EMF how big EMF will be produced while we move it from completely out, completely in. So what will be, what the initial flux through the coil?
0.
0, there's no magnetic field. Now when it's completely in, what will be the flux? B times A, 0.2 times area 0.01 equal 2 times 10 negative 3 Weber. So what will be the change of the flux?
2 times negative 0.
Both 0 become that, so change of the flux equal 3, the change of the flux equal 3 times, sorry, 3, where 3 comes from? I have no idea. 2 times 10 negative 3 Weber. And over what time it will happen?
1 second. 1 second.
1 second. So EMF, magnitude of EMF, which is, and we have one turn,
how do you know it's 1 second?
Because the side
because its side is 0.1 meter and it moves in with the speed 0.1 meter per second.
Yeah.
So we will have change EMF, change of flux over a period of time will be equal 2 times 10 negative 3 divided by 1 equal 2 times 10 negative 3 volt. So we have, yes?
So 1 volt equals 1 Weber.
Hmm?
Is volt the same as Weber? Like is it?
No. It's Webers over time. Just the time equal 1.
Okay. Yeah.
Okay, let's make it to move faster. Let's move it faster. Let's make it 0.2 meters per second. So then we'll have, how long it will take then to get it completely inside?
Half a second.
It will be 0.5. And that will becomes now not 2 times 10 negative 3, will be 4 times 10 in negative 3 volts. Make sense? So Weber is not volts, because we divided by 1 that we get the same number. So that's the magnitude. Now question is, in which direction current will flow in this coil while we're moving in? And that when we apply Lenz's law, and here are the steps that you must follow. Must follow. Step number one. Step number one is identify direction of the magnetic field. External magnetic field, external for the coil. So first, direction, external. In this case, it's given. What the direction of the external magnetic field? Into the ball. Second, is flux increasing or decreasing when we're moving it in? Flux increasing or decreasing?
Increase.
Flux increasing. And now, if flux increasing, how we say the Lenz's law that the induced current produce magnetic field that oppose change. So how we should act, the change is increase of the flux. How we should act to decrease, to oppose it?
Decrease.
Try to decrease. So in which direction should be magnetic field of the created by induced current? What will be the direction of induced magnetic field? In the opposite direction. If we have field in the board and increasing, how we can oppose it? To act opposite way, out of the page. So we have if flux increasing, be induced in opposite direction. So in this case, direction of the induced magnetic field is out of the page. Now let's use right-hand grip rule to identify direction of the current in the coil. What should be direction in the current in the coil to have magnetic field out of the page?
Anti-clockwise.
Has to be this way, which is anti-clockwise. That will be direction of the current. That's how we apply Lenz's law to find direction of the current. Make sense? Yes.
So when it decreases, still acts not
Now let's consider that we're moving this coil, we moved it in, and we're moving it out. We have what change? We identify flux will be when we're moving it out, flux will be decreasing. So if flux decreasing, what should be direction of the induced field to oppose it? In the same direction. If it's in the board and become smaller, decreasing, we need to push in the same direction to oppose this change. So you have induced, be induced in the page, and it will change direction of the current in the opposite way. So as you can see, we have current flowing in the opposite direction. I'm increasing flux, I'm decreasing flux. Increasing, decreasing. It changed in the opposite direction, as you can see. I'm moving magnet in, out, in, out. So current change direction. Make sense?
Yeah.
Now let's sketch a couple graphs. And that's where knowing of the at least basics of the calculus is very useful, of the differentiations. Any differentiation not needed. So in this case, when we have coil moving in the magnetic field, how the flux was changing over the time?
Decreasing.
No, when we were moving into the field.
Oh.
It was zero initially, then it was increasing at a steady rate because we were moving with a constant velocity. Then if we move through the magnetic field, so we have magnetic field here, and we move coil from here into and through. We move coil through the magnetic field. while it will be completely inside the magnetic field. Will be the flux changing? No. So you have flux, same. And then we're moving out, it's changing. This is how flux change over the time. Now EMF, the instantaneous EMF, as I said, equal and negative. This negative means length law, that the current in the opposite direction. That's what minus means. Minus n, in this case was 1, df, derivative of the flux over the time. So if you sketch now graph of EMF over the time, EMF, what is derivative of this straight line? It's a constant. It will be horizontal line. We have same gradient everywhere, so derivative here is constant. Now, what the derivative will be here? Zero, there is no change. So up to here, there is no EMF. And up to here, so, and then when we move in, but we have minus. Sorry, we have minus. So it's a negative derivative, so we have here. And now we have here. And that's what we will observe, EMF. No, this line you can draw, not necessary. We will have EMF, constant EMF when we move it in, no EMF while we're completely inside, and opposite sign of EMF when we're moving out. Because here we have gradient positive, here we have gradient negative, and EMF is a negative gradient of the flux graph. Now,
Right,
Does
so
it-
those lines, you draw it like a shape, those lines.
this is the
No, no.
gradient, negative gradient.
I'm saying the vertical
Those lines,
Yeah.
no, usually it's common practice to draw those lines.
Really?
You don't have to, but common practice to draw them. They don't have like any
Yeah,
special meanings.
Yeah.
Now, when I rotate the coil, so I'm not changing magnetic field, I change angle. And produce electricity. And how the flux will be changing now? How flux will be changing now over the time? If, let's say, we start from the position, we start, let's say, flux, magnetic field that way, coil positions like this. So flux will be big, maximum or minimum in this. We have all area, this all magnetic field, because in flux we can say number of line penetrating coil. Magnetic field that way, coil position like that, all lines going through the coil. So flux is maximum. And then we start rotate. What flux now? Now maximum but in the opposite direction, then again zero. So we will have flux change as a cosine graph. We have cosine graph. That's how flux change over the time. And you know that EMF is negative derivative. And what is the derivative of the cos theta?
Negative sign.
It's negative sine theta. But EMF is negative derivative. So what will be the graph of EMF? If we have this is a cosine graph, what will be negative derivative of this? Positive sign. Because derivative is negative sign, but we have negative derivative, so it will be positive sign graph.
Yeah, of course.
And that will be EMF.
What's a derivative or a cosine graph or a sine graph?
Hmm?
I don't know it.
Yeah, we have
Yeah, that I said where it will be advantage for people who know what derivative is.
Is it still possible?
How you can decide, then you just will have to make a note when the flux is cosine graph, the EMF will be sine graph. If you will have the flux sine graph, then EMF will be negative cosine. Because derivative of the sine is cos, negative derivative, negative cos. You just need to make a note when flux, graph of the flux is a cos, cosine, the EMF will be sine. Make sense?
When graph of it is what?
When we have the graph of the flux is cosine graph, graph of the EMF, induced EMF, will be sine graph.
Okay. Is the other way around as well?
If we will have flux if flux will be sine graph, what determine will be flux sine graph or cosine graph?
What position the coil starts in?
From what position it starts? If it starts from this position, when the flux is maximum, it will be cosine graph. It will start from this position, we start rotated from this position, flux through it is 0, so it will be sine graph. So is it sine or cosine graph determined just by the initial position? And sine and cos you can just translate it by pi on 2 or 90 degrees and they become the same graph. So if we have the graph of the flux against time is the sine graph, if it's a sine graph, then derivative of the sine is negative, is positive cos, but negative derivative, negative cos, so that will be the graph of the EMF, that will be EMF. What important observation we can see? When flux is maximum, EMF is 0. Here same thing, flux maximum, EMF 0. Flux 0, EMF is maximum. Why is that? Because rate of EMF is a rate of change of the flux. And here we have stationary point. There's no rate of change equals 0. Here the maximum rate of change. So we have rate of change maximum. We have maximum EMF. So that is pretty much sort of like introduction. Of course we'll do a lot of questions to better understand. But we covered the most important things. We covered the Faraday's law, Lenz's law, and you now prepared to do your holiday homework, which is on campus. It's all not from the booklet, as far as I remember, it's only from the textbook. Chapters of the textbook I will put on the campus together with the solutions, as well as the booklet and solutions to booklet you always can find on my website. So that's all. I think it's all for today. Like, subscribe and donate to help fight terrorist countries like Russia, Iran and Hamas. Support Ukraine and Israel.